Yeah. So it's 7 o'clock, first Sunday of the month, and welcome to this Chand-wise session. Chand-wise has started in 2009 Jan, and it happens now twice in a month. All odd Sundays are taken up by Chand-wise. 11 o'clock, we are here. First Sunday of the month, we are here. Third Sunday, we are at Nobel College, and very lately, especially during this COVID time, something on a fifth Sunday, we show you something from our lab. So directly from the lab, fun from the lab. And the next Chand-wise here is going to be by Sneha Hegde, and it's about the role of the myriad role of the mighty mitochondria. You know what mitochondria is? It's the power of the cell. We'll come to that when Sneha speaks to us. The third Chand-wise in this month, 21st, we have yet to decide whether we want to do a theoretical part only or we want to have some hands-on activity. So we have not decided. We will declare soon. So today we have Sourav Chatterjee with us. He did his bachelor's at Jabalpur University, then he went to IIT, did his master's and went out to Marcus University, and then he's come back to India like all very, very patriotic Indians. And I'm talking patriotic because this is the 75th year of our freedom. So Sourav will tell us more about the topic. We're all interested. I can see young crowd over here. Usually the college kids normally don't come, but well, black holes, interesting, right? Fine. I thought stay between you and him. Sourav, what do you say?
Thank you so much. Thank you for coming here. I know that Sunday sleeps are special. You braved the rain and did not sleep too long, and you came here. So now I really have to make it worth your while. Right? So today we are going to talk about merging black holes, and mainly the focus will be how to make merging black holes. And after this talk, you will know that it's not very simple to have two black holes and have them in a configuration so that they merge within the age of the universe. Okay. So let's go ahead. So if you have questions, just ask. I like a lot of interactions. And if you don't understand something, you can always ask. There is no bad question. Every question is good. Okay. So we are here because we want to have fun. We want to learn. So of course, even if you are not in astronomy, you probably know that the 2017 Nobel Prize was awarded because scientists discovered gravitational waves. And this discovery, or the gravitational waves that they discovered, came because two black holes merged very, very far away from us, but they merged and we discovered the gravitational waves. Okay. And this created a lot of interest, both in the scientific community. Well, the scientists were already interested, but it made it even more interesting. And even the public got very excited about, how black holes form, what kinds of black holes are there, how black holes merge, when they merge, what kind of signals they give, and how do you detect them. Okay. So the plan of today's talk is it has like two major groups. The first one is I will very briefly, very superficially tell you about what gravitational waves are, okay, and how what kinds of gravitational waves there are, what you are actually measuring, etc. Okay. Don't worry, I will not talk about GR because that's not the spirit of this talk. If you want to learn about GR, that's a separate proposition altogether, and I would love to teach you at some point. But today we are not going to do that. And the second group is basically once we know what gravitational waves are and what the gravitational waves that we have detected so far, I'm going to talk about how in two major different ways you can form these objects that would merge and then can be detected. Okay? And the take-home points from today, so after this lecture, if you remember how black holes form, and if you remember how binary black holes form that merge, then you have followed this very nicely, and we are all happy. Okay? So that's our goal for today. So what are gravitational waves? So you probably have heard about the so-called idea of space-time. So time and space are not very different from each other, and instead of space and time separately, we should be thinking about space-time as our coordinate system. This was the contribution of Einstein, and if you understand space-time and how it evolves around mass, then we know that when two very massive objects are very close to each other and they are orbiting each other, then that creates ripples in the space-time. So it's very similar to if you drop a stone in a pond. So let's imagine that there is no air, there are no ripples on the pond. You drop a stone and it creates ripples. Okay, and the ripples radiate away radially from where you have dropped the stone. Okay, it's very similar to that, and this is how it looks. And this is a actual simulation that they created a movie out of. So here you are seeing, you are barely seeing actually. Can we just get rid of this light? I'm sorry. So can you see these two black things? Okay. So imagine that these two are black holes and they are just orbiting each other. And over time, they are losing enormous amount of energy by creating these ripples in the space-time. And at some point they merge. Okay. These are classical waves. These are classical waves.
And we consider that the speed of this wave will be equivalent to our speed of light.
Yes. So if you do the calculations in GR, this wave is very similar to electromagnetic waves. So the speed of this wave in vacuum is equal to c, and this is also a transverse wave.
It's also transverse. That means it is creating a ripple, and that ripple is crossing across the space-time, and that ripple is passing to the same speed of light.
Yes, yes, until it encounters matter.
Sorry, yeah.
General relativity. Yeah. Okay, so that's what we are detecting, and that's what this talk is about. Okay.
Okay, just wait.
Yeah.
Can't we just consider as quantization, like we call that it's because graviton is moving or something like that, and we have detected the graviton in place of detecting the wave.
You know, this is one of the most burning questions in physics in general. How do you quantize gravity? So there are basically, if you think about the, big fathers of the pillars of physics, there is Einstein and there is Bohr. Okay, so there is this quantum lineage of physics, and there is this classical lineage of physics, and so far these two lineages have not merged. Okay, and there are many different theories, and which theory is actually correct is not known. So one of the professors in Tata Institute, if you speak with him, he will say that neither of these theories are completely correct. Both of these fathers of physics actually has a father, but yeah, so we don't know how to quantize gravity. Yes. So I think I'm not an expert of string theory, but
For the benefit of online audience, could you repeat the question, whatever they are?
Of course.
Online people also. Thank you.
So the question is, can string theory explain this? String theory, the way you should think about any theory in science is, can the string theory explain it? Is not the right question. String theory must explain it, okay? And the question is string theory consistent with this thing that we have observed? And some string theories are consistent, okay? But the implications are not yet known. So for example, if you simply assume general relativity as the truth or the theory that governs this physics, and then nothing else is needed to explain the observations that we have. And the way this is done is they have predictions from general theory of relativity, and they try to match with very high accuracy what they have observed. And the question is, are there any portions of the observation that cannot be quite explained by the general theory of relativity? And that's the area where you have need for different physical paradigms, okay? So far, the observations do not need anything else apart from general theory of relativity, okay? All right, should I move on? Okay, so how do this, is this bothering you on the top? What?
The grid.
Which one? I actually cannot reach. I just want to hide it.
Find out.
Okay. Okay, let's do this for now. Okay, so how does this gravitational wave react or interact with matter? Okay, so imagine that in space-time, we have these units of distances. It's like if you have a scale, there will be these markings, and all these markings will have some unit of distance. So imagine that you have some unit of distance, and you are thinking of a ring of mass, okay, like this. And this is a perfect circle. So the distance from the center to this side and center to that side are equal, okay? Now, when a gravitational wave passes through, it bends these masses kind of like this, okay? So I have a hula hoop for this. So if you have a ring of mass, and let's say the gravitational wave passes through this, it'll be like this, okay? And it'll keep on doing this. And there can be different polarizations, like the electromagnetic wave, okay? So for example, it can be like this, or this, okay? So these are the two polarizations. And if you, all of them are perpendicular to the direction of the motion.
Two polarizations will also be perpendicular.
Yes, it's very similar to electromagnetic wave. The only difference is, in electromagnetic wave, you need an electric dipole that creates the wave. In gravity, you need a quadrupole, okay? And a quadrupole comes from when something is not exactly spherical, okay? So now imagine what. So a quadrupole of mass is non-zero when something is not exactly spherical, okay? And it's changing, okay? So now let's try to think about what are the different things that can create gravitational waves, okay? So for example, a star explodes, a supernova, okay? And that is not spherical at all. There are all kinds of asymmetry. and it's a rapid change in the mass distribution that will create a gravitational wave. We have not detected it. Then imagine that there are two masses, like the black holes in that movie, and they are just orbiting each other, right? So this is not at all spherical. And the masses are changing position very rapidly. This will create a quadrupole, and this will create gravitational waves. These are the kinds of gravitational waves that we have seen or observed, okay? So now let's see what is the effect of these gravitational waves when it passes mass. For example, of course, now we know that binary black holes exist. We have seen supernova to explode. So these gravitational waves are being emitted throughout the universe. And since it's like light or electromagnetic wave, it's just propagating throughout the universe, right? So they are all reaching us, going through us all the time, okay? So the question is, and we are massive, so we are interacting with these waves. So the question is, can we feel it? So let's figure out how big the ripples are. What are the amplitudes of these ripples? So the way we can estimate what is the effect is by measuring this change, right? So this is the normal thing if there is no gravitational wave, and the red is the abnormal thing because of the gravitational wave. And this change is dl, okay? And in science, you should always think in terms of ratios, okay? That makes it not depend on units. So let's take the ratio dl over L, and we define the quantity h. This is called the strain of the gravitational wave. And we have a 2 here because there is dl here, dl there, okay? So we are going to see some numbers for this h. And this is the h that we measure, okay? What is h? So this is for those who like math, okay? It is a product of this term. This is the mass term, okay? So this is the gravitational constant, g. This is the mass of the whatever is emitting the gravitational wave. And this is the speed of light in vacuum. This is the velocity of the mass that's moving. And this is, so there is this v square over c square term. And then the further the mass is, the lower the effect is, right? So it's the same as the further the light is, the dimmer it looks, okay? So that's how you measure this quantity h. And that is just 2 times dl over L. Yes, you have a question. Yes, the mass that is emitting the gravitational wave. That is the speed of that mass. Okay.
This formula is for a single mass if we are considering only one m, or is it for a couple of masses? And the detection that we have for gravitation is from 2 masses. So, like, what is the m for?
This is actually a function of both m. I did not want to make it too complicated. You can think of it as a characteristic mass. Okay.
D square by c square is very less.
Usually.
That's why we cannot detect. So you have to make it higher number to detect it at such a large distance.
Exactly. So, for example, yes.
Some of these questions are very special questions. I would like to have general questions, okay, but otherwise, all these special questions, like this, particularly equation physics, not very commonly appearing in the minds of other people. So we can see them at the end, so that let the speaker go through the entire flow of the talk. The special questions can come in.
Okay, since you asked, so for example, if I just run around I will emit gravitational waves. But I can, my velocity will be very small compared to c, okay? But when two black holes merge, just before they merge, the orbital velocity of the black holes is very close to c. And this quantity becomes very close to 1, okay? That's why we need these extreme energetic sources to detect them, okay? Now let's estimate some number. And I'm giving you an example of, so I have made the two masses equal just for simplicity. So this is roughly the average mass of the first gravitational wave that we have detected, okay? And this is the distance of that source, okay? These are all measured. For this system, so this was one of the very, very energetic gravitational waves that we have detected, okay? Of course, the first detection always is the strongest, right? Can any of you guess what H would be? Like, is it like a grain of sand? Is it like, yes? It's not mass, it's a fractional change in length. So let's say that I am standing, okay? I'm roughly 6 feet, okay? How much will my length and breadth change because of this gravitational wave? Your guess? Getting warmer? Yes? Larger atom. Okay. So if okay.
Assuming the radius of an atom is 10 raised to minus 10 or 10 raised to minus 14 meters, is that
Okay.
much worse than
So this is what we need to detect and have detected, right? So this is just amazing. This is just amazing. Although this is not the talk where I talk about the detector itself, but the detector is just amazing. It can detect a car braking 20, 30 kilometers away from the detector because the car braking creates ripples on the ground and it goes and encounters with the detector. So they have to get rid of all of this noise to actually detect this thing. So just to give you an example, so forget about my length, okay? So imagine the Earth, okay? And imagine that the Earth is a sphere, so we have a diameter, okay? So the diameter of the Earth will change by about 1/100th of a nucleus, okay? So that's the signal, and they have detected.
Yeah. What's the margin of error? I mean, the instrument which is measuring this, what can be the error possible?
That's a very, very involved. So the question is, when LIGO detects the gravitational wave, what is the margin of error? The reason why this is a very involved question is error in what? Okay, so there are various sources of errors, and different detections will have different quality and different magnitudes of these different sources of errors. And they normally, if you know this, so they normally go through a Bayesian marginalization. Okay, so I am now throwing jargon at you because this is an involved question. Bayesian marginalization, and typically the masses that they measure. So the chart mass is what they measure. This is a function of the two masses. That is the most well measured quantity. Typically, the error bar is within 1 sigma is about 10 to 20%.
There is an online question. What is M?
Can you read the question?
That's the question. What is M dot? M 30.
30. This. Yes. Thank you, online questioner. So when I will show this symbol many times. So whenever you see something like a circle and a dot in the middle, this means this is for the sun. Okay. So M then subscript this thing means mass of the sun. So I am talking about black holes that are 30 times the mass of the sun. And if they merge 1.3 billion light years away, so this is the distance from where light takes 1.3 billion years to reach us. So it's that far, then the strain will be like this. And I have told you the magnitude of the strain. So the diameter of the Earth will change by about 100th of a nucleus. Just to put in perspective how tiny the signal is and how hard to detect this signal is, the moon creates a tidal strain of 1 meter. Okay, so this is how small it is. Yes, you had a quick question. I'm coming to that. So the way they detect it is you have these black holes sending out ripples, and there is a very powerful laser that goes and bounces in two light chambers in two sides. And when these two lengths are exactly equal, in the detector sitting here, there will be no light. But if the lengths are changing, then the two beams will come slightly at different times, come back, and then there will these two waves will not exactly cancel each other, and you will see some light. Okay, that's how they detect it, and this is called an interferometer. Okay, if you're a college student, you probably have seen this. I don't want to get into this too much. Okay, all right. So using interferometry, you can measure very small changes in this. And this is a real image of one of these LIGO detectors. Okay, and this is the observatory, and these are the two arms. The arms are 4 kilometers long, and there are several of these detectors. So the two US ones are this LIGO at Hanford and LIGO at Livingston. This GO600 is a much smaller detector. It usually does not get analyzed for particular detections. This is mostly used for experiments and teaching. The European detector that does contribute to detections is Vargo, and Kagra is the Japanese detector, and this also gets analyzed whenever there is a signal. And the way you know that this is not noise and it's a signal is by requiring that all of these detectors must have detected something. Okay, and then you can do very complex analysis to figure out the directionality of the detection. And what's really exciting is there is going to be a LIGO India as well. Okay, and I don't know the exact update on when it's coming, but the land is there. They have started digging, and hopefully very soon we will have a detector in India.
Which place are you using?
I think it's in MP. Yes. So the question is, can you put a detector wherever you want, and based on whatever you think is scientifically more rewarding? The answer is no. So as you can imagine, that you are basically measuring small changes in distance, and these are all ground-based detectors, so they are all sitting on Earth. So, for example, you have to figure out whether the region that you are interested in is very earthquake-prone or not. Okay, so this is an example, but there are probably like thousands of different lists that you need to worry about. But in general, if science were the only driving factor, the places that you want to keep these detectors must be really far away. Okay, and then that gives you the most scientific advantage. So that's why a lot of people are very excited with LIGO India, because if you think about it, this US LIGO detectors and India LIGO detector are kind of the furthest that you can go in on Earth. So that's all about what are gravitational waves, how do you detect them, what are the detectors that have detected gravitational waves, okay? And there are some planned. Now, we have talked about the effects of gravitational waves on changes in distance, okay? So that is where the observer is standing. Now let's go to where the source is, okay? And where the source is, these are some of the most mind-boggling energetic events that universe ever produces, okay? So let's look at some numbers. So again, I come back to the first detection, okay? So this is called GW 150914. If you read in news that this is the name of a gravitational wave, then you feel like, oh, the scientists do not know how to name things. Why not Charles? Why not, okay, some other name, okay? So the way it is the name is GW is gravitational waves. And then 15 is the year, 09 is the month, 14 is the date. This is the date of the event, not the announcement. Okay? That's how the naming works. And I have already told you that these guys merged 1.3 billion light years away. Okay. Now let's look at the energy. So when they merged, they emitted gravitational waves. So they must have lost energy, right? The amount of energy they lost is this. So it's like converting 3 times the mass of the sun into energy. Okay.
Since this is emitting energy, so this energy must have been transformed not only in the form of gravitational wave, but in other electromagnetic wave also. Have we correlated these type of events in other systems all worldwide?
So the question is, these merger is creating a lot of energy, emitting a lot of energy. Is this energy being emitted only in gravitational waves, or is it emitted in other waves as well? Okay. So if it's 2 black holes, are you answering the question or asking a question? Okay. 1 second. So if both of these are black holes, then nothing can emit the event horizon of the black hole. So it will only emit gravitational waves. However, we have also detected neutron stars merging and possibly black hole merging with neutron star. In those cases, at least there is one case where 2 neutron stars merged pretty close from us. In that case, we have detected it in gravitational waves, gamma rays, X-ray, optical, infrared, micro, radio, everything, the whole spectrum. Okay. Yes, your question. So, I understood your question. So the question is, when these two things merge and it's emitting energy, is it only emitting waves, or is it also emitting some energy in some other form, like a explosion or something? Okay. So it will, in about maybe 6-7 years, you will know when you do this equation, then there is one form of, so you are getting the energy loss from different ways, and there is only one form that is not zero at infinity. That form is the wave. So at a large distance, you only see wave. At very short distances, it is not pure wave. It can have other manifestations. But of course, we're not there. Okay, very good question.
So when this event happen in time, our concept of normal concept, what is the time the event actually happens?
You tell me. So I told you that it is it happened 1.3 billion light years away. When did these two merge?
Because light is that long.
Yes, exactly. Yes. But a different question is, when did these black holes form? Okay, that has a lot of uncertainty. Let me finish this thing. I am loving it, by the way.
I'd love to hear.
Okay, so let's put it in perspective. What happens when you convert 3 solar mass into energy? So the power radiated by this event at the peak is this. Watt is the power, unit of power. And compare that with the power radiated by the sun. Okay. So it emitted for a few milliseconds 10 to the 23 times the power emitted by the sun. Okay. This is more power than the total power radiated by all stars in the observable universe. A single event for a few milliseconds. Okay. That's how energetic this event is. Yes, your question. So the question is, this is a lot of energy. Can we somehow harness it? Okay. Not sitting on Earth, because you see the rate of the length change, the effect is like changing the diameter of Earth by 1/100th of a nucleus, right? So sitting on Earth, we cannot do it. Possible? So the question is, can this, now we cannot, but maybe in future, can we harness this energy? And, you know, I'm a scientist, so I will never say that it's not possible. The question is, can we in future build something that can harness this energy? Think about it. I don't know anyway. You had a question? Yes.
I actually want to answer this question. I mean, if you look at it from another perspective, it's black holes that do.
Black holes? What?
I mean, you can't see that it is a black hole that you're dealing with. They're not dealing with the sun or something a lot less weaker and a lot less easier to harness the energy because this is the sun's energy amplified so many times. So to harness it would be an inhumane task.
Well, I'm not saying no. I'm not saying yes. Think about it. Yeah. So, so these are the what we have detected so far. We being them. I didn't. So this is the mass axis, and these are just a beautiful arrangement of all these masses. So what you are seeing is these two black holes merged to create that. Okay. So of course there are a lot of astrophysics and cosmological implications of these detections, and that's the topic of maybe some other child life. Okay. But I promised you that I will tell you how you make binary black holes that merge within a Hubble time. Hubble time is the age of the universe. Okay. So the most straightforward, at least conceptually, way to form binary black holes is you start with two very massive stars in a binary. Okay. And then both these stars become black holes and remain in this binary. And then as they are moving, of course, they're emitting some energy. And over time, the orbit shrinks because it's losing energy. And as an orbit loses energy, it shrinks. And at some point, they just come too close to each other and merge. Okay. Now, there are many problems in this. Okay. And you have to be an exquisite chef to cook up binary black holes that merge within the age of the universe. Okay. So what are the challenges? Before I get into that, first let me give a very quick review of a star's life. Okay. So how do stars live and die? And especially the very massive stars really live and die like the really talented stars. Like they live bright, die young, and create a legacy. So massive stars are like this. So in any star, you just start with a blob of gas, and gravity is trying to pull everything inward. And in the center, at the very dense part of the star, you have nuclear fusion. So fusion bombs exploding, okay, every second, many of them. That creates a lot of energy, that creates a lot of temperature. And when you increase the temperature of something or some gas, then its pressure increases, right? And pressure, as we know, is trying to push everything outward. When the gravity and the pressure are in balance, then we have the so-called main sequence of a star. So this is the time of a star's life where it is reasonably stable. This is the longest time of a star. This is when a star is making all those movies, playing brilliantly or something. Okay, in balance. Now, when the balance goes off, things start to happen very quickly. So near the end of the life of a star, near the end of the main sequence, it has converted all the hydrogen into heavier nuclei. I don't want to get into the details of the thermonuclear chemistry here, but imagine that you have finished all your fuel. So you cannot easily make energy by fusing nuclei anymore, okay? So you cannot maintain the temperature and the pressure that kept you stable. What happens then? So imagine that this is the part that is the core, where it was burning all those thermonuclear reactions, and it created, there is no hydrogen anymore, and only heavier nuclei. So there is no pressure, gravity wins, and this happens. So this is the core, that is the envelope. So the core contracts because of gravity, and that creates a lot of energy because things falling. So a lot of energy is released. That energy is absorbed by the envelope. The envelope becomes really big. This is called the giant phase of a star. Okay. Now there are a few important things that you need to remember. Okay. So if the mass of the core is less than about 1.4 times the mass of the sun, then this core will end up creating a white dwarf. So our sun, when it dies, will become a white dwarf. If it is between, say, 1.4 times the mass of the sun and less than 2 to 3 times the mass of the sun, this number is not very well known, okay? Then it becomes a neutron star. If it is above this limit, then it creates a black hole, okay? And the other thing that I need you to remember to understand the later part of this talk is that the size of the star becomes really huge, okay, for the stars that create black holes. So the size can become several hundred to even 1,000 times the size of the sun. That creates a lot of trouble to make merging binary black holes, and I will tell you why. So let's consider this part, okay? So 2 stars, they become 2 black holes. Let's consider this phase. So first of all, the binary must not break, because then the stars just don't talk to each other, they just fly away. So there are a few things that happen. So every massive star loses a lot of mass through wind. When stars lose mass, then the orbit becomes larger and larger. And then when stars explode through supernova and form a black hole, it also gets a kick. And these kicks can also break the binary. And we really do not want the stars to merge. We want them first to make the black holes and then want the black holes to merge, okay? And I told you that before the stars become black holes, they can become 1,000 times the size of the sun. So you need at least 2 times 1,000 times the size of the sun separation, at least, for the stars to begin with. And then, orbits expand because the mass loss. So you cannot have binaries that are very close to each other to begin with that will end up creating binary black holes that would merge. Yes, your question.
If the stars are massive, they have to be like further apart, so that the envelope will go to the star. But then if they're really far away, then they also have to be more massive to actually keep in the binary. Like, so then have you actually seen binary stars turn into black holes?
No, we have not seen binary stars turning into binary black holes because that happens very fast. So catching them in the act is very low probability. You have a quick question?
So, how you can detect when the black hole is first? Do you use some techniques to sense other kind of astronomical measures? For example, could we detect when say black holes are close to merging, so that in case we miss the actual event, we can detect beforehand
Okay, what was your question? So I will combine the two answers. Okay, so it can happen, and we have detected black holes merging with neutron stars. Okay. Your question was, can we detect them before merger? We are detecting them before merger. Okay, so the detectors that we have currently can detect waves higher than 10 hertz. Okay, higher than 10 hertz means that the orbital period is 20 hertz. Okay, so we are detecting them right before merger, but the farther they are, the lower the signal. Remember the v square over c square term? So the further they are, the slower they're moving. So detecting them is the harder. Okay. There is actually a planned detector that will be in space that has much longer arms that is specifically designed to detect mergers like this when they are still really far apart. But then the problem is, remember the mass term? So when they are really far apart, the signal is low. And the way to boost the signal is by increasing the masses. And that detector will be particularly sensitive to detection of supermassive black hole mergers. So black holes that are about 1 million solar mass. Yes.
So when we talk about supermassive black holes, Milky Way and Andromeda both have supermassive black holes, and we have predicted that they will be merging. So are they in a binary system? Like, are they already orbiting each other? And can we like using like high technology, like perhaps James Webb or something like that, to like either predict how they will merge, or how like they got into the binary system to begin? So is that possible? Like, even predicting and capacity of our own disease.
So the question is, we know that the Milky Way as well as Andromeda have supermassive black holes each in their centers, and the Andromeda and Milky Way are in a collision course. So at some point, will these two supermassive black holes merge? The answer is yes. The details are also predicted. This is a completely different and really interesting story. So there is a lot of dynamics that happens when two galaxies merge, and exactly how two black holes slowly sink in the combined potential and find each other. But that's, we can talk about that later. Okay, so the other thing that we need to worry about is the second step. So black hole binary must be compact enough to merge. Okay, and I will give you some numbers to explain how strong this constraint is. Okay, so forgive me about some equations. I will explain this to you. So imagine that the distance between the two black holes in orbit is 2 times a. Okay, at that time, the rate of change of this separation. So through gravitational wave radiation, you need to get it from A to 0. Okay, that's when they merge. So the rate of change of this separation is proportional to something like a mass cubed. Okay, so mu is like mass unit, and this is the total mass of these two objects. It's the square of that. Okay, so something like a mass cubed and divided by the separation cubed. Okay, ignore the eccentricities for now. Okay, how elliptic the orbit, ignore that. So when they are reasonably far apart, for the same mass, when they are far apart, it takes forever for them to release enough energy and shrink the orbit. But when they're close, it happens really quickly. Okay? So let's put this in context. So this, on the y-axis, I'm showing you in spiral time. So starting from any separation, how long will it take for the two black holes to merge? Okay, that is this time. And the unit is in billion years. And in the x-axis, I'm showing you the separation in units of the size of the star, of the sun. Okay, and this line denotes the age of the universe. Okay, anything here will not merge in this universe. So we're interested in this magenta area. Let's read this number. I know that this is kind of small. This number is 20 times the sun's size. But what do we know from the size of massive stars? They can be 1,000 times the size of the sun, right? So if you want the binaries to not merge before they get a chance to form black holes, they need to be somewhere here. And this is a logarithmic scale, okay? So this point is 1/10 of this point. So you have to form the binary or the stars here. And then unless you can bring it all the way here. So this is a shrinking of 3 orders of magnitude. Okay, starting from 1,000, going to like a few. Okay, unless you can manage that, there is no hope. They may form black hole binary, but these black hole binary will not merge ever. So what magic nature does to manage this? This is called a common envelope evolution. Okay, and that shrinks the orbit very rapidly. So what is a common envelope? So let's think about two stars. So both stars have gravity and they are pulling each other. And if you calculate when the gravity of one star becomes so strong to the matter of the other star that the other star is shredded away. So the one star just strips of mass and eats the other star, okay? So that's this line. So if this star becomes bigger than this line, mass will flow from this star to that star and vice versa. So I'm showing it here. So when stars expand in the giant stage, right? So stars expand and they can, in principle, become bigger than this line, and then mass flows from this star and tries to fall onto this star. Okay, but so this is like eating, right? Someone is giving food and you are eating. But if someone gives you food much faster than you can eat, it happens to maybe you still remember when you were much younger, your parents probably fed you, and sometimes you just didn't finish what's in your mouth yet because maybe you were distracted watching some cartoon or whatever, and your parent wants to feed you more. It doesn't work, right? Same thing happens to a star. Okay, so if the mass flow is too much, too fast compared to how quickly you can eat it, then something like this happens. There is mass everywhere, and this is called a common envelope. So there is the envelope of both stars, they merge, and these two cores are moving around inside a common envelope. Okay, so when this happens, the gas in the common envelope creates a lot of damping in motion. So for example, if you have a wind, it's harder to cycle, right? Because you have that barrier. The same thing happens to the pores, and the orbit shrink. Okay. So this is how we believe black holes can shrink. So I am going a little fast here. So this is a possible story of how the first gravitational wave happened. The two black holes came very close to each other. So you start with very massive stars. There was first a Rho slope overflow. So this star became too big for its own good. It donated some mass here and then kept doing it. Then this became a black hole. This is still a main sequence star. And you see, this is the separation, okay? So this is 3,700 times the size of the sun, okay? Roughly, in our estimates, this is how separated they should be. And that's exactly what we see here. So this is a real simulation, okay? And then this becomes big, and it starts a common envelope because it starts giving mass at such a high rate that this black hole cannot accrete. So it creates a common envelope. After the common envelope, it shrinks from 3,780 times the sun's size to something like a 43.8 times the sun's size. And it happens rather quickly. After this star becomes a black hole. And at this time, the separation is only about 50 times the size of the sun. And then it merges after a few billion years. Okay.
What's the number and size of the
Our annoying panel is blocking things. So this column is time in million years. This column is separation in size of the sun. And this column is the eccentricity, how elliptic the orbit is. Okay? You don't have to worry about the eccentricity for this talk. So the real magic happens here. So you go from roughly of order 4,000 times the size of the sun, the separation, it goes to like a 50 times the size of the sun. Okay? And that is the most crucial part of creating a marching binary black hole. Okay? And unfortunately, this is also the stage that has the least constraints because we cannot really observe things in this phase, and it's very, very hard to solve from first principles. So now I come to the second recipe, okay? And this is dynamical formation in dense stellar systems. What do I mean by dense stellar systems? So these are clusters of stars. For example, if we look up in the sky, there are these star clusters. There are some open clusters and globular clusters. So they look like this. Okay, these are fascinating objects. Really beautiful. If you get your hands on a telescope and go to a dark place, you can see some of these on a clear night. Now, what happens when you pack things very close to each other? Okay, so the densities in these clusters are like if I put 1 million stars between the sun and the Proxima Centauri. So Proxima Centauri is the closest star from the sun, right? So imagine that you put 1 million stars there. Okay, that's how dense this is. Okay? When you increase density, we all know about crowds, right? So things happen in crowd. So stars come very close to each other. They interact gravitationally with each other, and a lot of interesting dynamical objects form. Stars collide with each other, they get deflected, and so on. Okay, so this is, by the way, a movie created from a real numerical simulation. Okay, so this really has about 1 million stars that are interacting gravitationally with each other and creating lots of collisions and stuff. Okay. Now, what happens? This is the crowd. So in a crowd, people collide with each other. So you can, so that's 1 million stars very close to each other and interact gravitationally. And dynamical processes can bring black holes together and create new binaries. So this is a situation. So in the recipe before, you started with 2 stars that were bound to each other from the beginning. These 2 stars created black holes, and these black holes merged. Okay. In this case, the black holes can be single stars. So some stars somewhere in the cluster formed a black hole. Some other stars somewhere else in the cluster formed a black hole. These black holes find each other, interact, and create new binaries. Okay, so let's talk about how this works. So there are 2 physical processes. There are several physical processes that are important to understand how star clusters evolve. But the 2 processes that I want you to understand for this talk are coming. Okay. So the first one is 2 stars can come close enough to each other and just scatter each other. Okay. So if you throw one mass to another mass, they will just scatter. Okay? One thing. So when they scatter, something really peculiar happens. And this is a property of any bound system. Okay. So normally, if you give energy to someone, it speeds up, right? And if you take energy out, it slows down. In a gravitationally bound system, exactly the opposite happens. If you take away energy, it speeds up. Why? Because it is already in a potential. If you take away energy, it sinks into the potential and it speeds up. So for example, if you have a satellite in orbit to Earth and you hit the brake, the satellite simply moves to an orbit that is closer to Earth and speeds up. Okay. And that is very important, okay, because this creates a runaway process. So if because of that scattering, some star loses energy, it sinks deeper into the potential, it speeds up, and now it has more energy to give. Okay, and that creates a runaway process. So something, and typically, the more massive object is the one that loses energy. Okay, so, and then since it's a runaway process, the more massive object just keeps sinking to the bottom of the potential. This is, by the way, so it sounds all very fascinating, right? But we see it every day. Do you see dust settling on the floor? This is exactly this. So dust is interacting randomly with all air molecules. Dust is more massive than the air molecules. So dust loses energy and sinks into the potential of the Earth. And where does it settle? On the floor, because it cannot go any further, right? So this is the same thing. Now imagine black holes are more massive than a typical star. So a black hole, after these random interactions, will start sinking. And where will it sink? At the center of the cluster, because that's the bottom of the potential for the cluster. So imagine in a star cluster, you have black holes created all over the place. Where will they go? Yes. So you do not need to start with 2 stars that were initially close to each other to form the 2 black holes. Okay? That's the major difference. I think it will be done in 5 minutes. 5 minutes? Yeah, with a question. Okay, so let's see So if you have a mix of black holes and stars, so black dots are black holes, yellow are stars, this happens, okay? So you don't have to worry about creating the binary black hole. The star cluster, through dynamical processes, takes care of it. I really need to finish. There will be, don't worry, I will answer all your questions after the break, okay? Now, what happens when the black holes find each other, okay? So for example, you came from all over Mumbai, I'm hoping, okay? And we are all gathered here because of something, this giant one, right? So now we are interacting. So the black holes that normally would not even know the existence of other black holes, so the other black holes, all find them in the center of the cluster, where the density is the maximum, so they interact gravitationally with each other. What kinds of interactions, right? Now, star clusters also have the normal binary. So the first recipe, I was talking about the normal binaries of stars. So the binaries are bigger than normal stars. So black holes interact with the binaries more often than normal stars. And something like this happens. So you see, a binary comes and interacts with, let's say that this is a black hole. This is something that we call binary single encounter, okay? And this, by the way, is a real simulation. So this movie is created after solving all these forces. And this is real. This happens all the time in the centers of clusters. So what do you see in the end? In the end, you see there is a swap, okay? So the blue entered into the binary, picking out one of these rays, okay? Now, a more massive object has a higher chance of getting into the binary, picking out a lower mass object from the binary. So if a black hole, a 10 solar mass black hole, comes and interacts with two 1 solar mass stars, then one of these 1 solar mass stars will be picked out, and now the single black hole finds itself into a binary with a 1 solar mass. Now imagine that this binary now interacts with another black hole, and then that black hole will pick out the star, and now you have two black holes in a binary, okay? Now, once you have created the big boss of binary, two massive black holes in a binary, it does not get picked up because the other stars are lower mass. But these encounters do one important thing. It takes away energy from the binary and it makes it shrink. So here I'm saying exchange interactions usually get the lightest star in favor of the heavier star, okay? And if you do it 2 times with 2 black holes, then you have a black hole binary. And this is a very hard to break binary because it's very massive. And further encounters do not break the black hole binary, it simply makes the orbit shrink. How long can you make the orbit shrink? Before it gets ejected from the cluster. And also these binaries typically have very high sensitivity, so very elliptic. Ignore that. And how long can you do this before the black hole binary is ejected from the system? Okay. Why will it be ejected? Because after every encounter, there is a recoil, right? So if the ejected star is moving in this direction, the binary will move in that direction, right? Simple Newton's third law or second law. Third and second law are the same law. So the process is basically most massive black holes sink to the center. And this also creates kind of a unique feature of dynamically assembled black hole binary. So it's almost like a filter. So you only allow the most massive black holes form the black hole binary, and then they either merge in the cluster or get ejected and merge at the time. And then you send the next batch and an X back, kind of like this, okay? And only after the black holes are significantly depleted through ejections and mergers, etc., the neutron stars that are typically much lower mass than black holes can come and interact. Okay? And this can go on until the binary is ejected due to recoil. Okay. I thought that I will talk about this a little bit, but let's keep this. Now, let's look at this plot. Okay. What I'm showing you here is the mass of the cluster in the x-axis. Okay. And this is the some representative time scale, like how long different process takes inside that cluster or that given mass. Okay, that's what I'm talking. Now, this green dashed line is telling you the time it takes for black holes to sink. Okay, so the way it works is the more massive clusters will have more stars, and the black holes will sink later. Okay? So if the cluster is very low mass, black hole will sink very quickly. Now, this blue line is showing you the in-spiral time, or how close to each other these black holes are once they have formed before the recoil takes it out of the cluster. Okay, so the reason why it goes this way is the escape speed depends on the mass of the cluster. Okay, now although in a low mass cluster the black holes can find each other very quickly, it's very easy to eject that black hole binary from a low mass cluster, right? So the black holes do not get enough chance to shrink enough and be eligible to merge within the age of the universe. And this red line that does not really contribute much is the interaction time scale, how often the black holes interact with other binaries, the movie that I showed you. So what you are seeing is it's quite often, and it does not really hamper the process. But this V shape is created by the fact that in low mass clusters, it's very easy to get the black holes together, but it's not easy to make them compact enough, the binary compact enough. In very high mass clusters, it's very easy to make the black holes compact, but it takes a bit of time to collect the black holes. Okay, and the competition between the two creates this V shape. So the smaller this time scale, the easier it is to make margin black holes. Okay. Now, what's really cool is somehow nature knew about all this. Okay, and if you look at the mass function of globular clusters, so this is how many these dense clusters you have as a function of mass. That looks kind of like this. So there are more clusters in the mass range, like 100,000 solar mass to a million solar mass range, than other masses. Okay. So this is kind of curious that exactly where it's really efficient to make binary black holes that would merge within a Hubble time, that's exactly where we find most of the star clusters. And as a result, nature has found a way to create these binary black holes through dynamical processes as well as through isolated evolution of binaries. So just to summarize, I showed you what the take-home points are at the beginning. So again, they are here. So if you remember, like 2 months from now, what gravitational waves are, how small the ripples actually are, and how energetic they are. Then it's a success. I talked about very quickly how stars evolve and how black holes form. And I talked about how in an isolated binary, you can form marginal binary black holes. And there the problem is you have to start with really far apart, and then you have to go through a common envelope that shrinks the orbit. And finally, I talked about in dense star clusters, like globular clusters, or a cluster in the center of the Milky Way or other galaxies, dynamical processes can also bring black holes together, form binaries through these dynamical processes, and they can merge. Okay. There are other less common recipes, but that's maybe for offline speaking. It was a pleasure talking to you today. Thank you all.
Before we break for the tea break, there are a couple of questions from one Abhinav Chaudhary from YouTube. Sorry. Can we detect high energy neutrinos coming out of the black hole binary? And the second question by the same person is, do merging black holes give us some hint about existence of quantum gravity? We'll address these two questions and then break for tea break. We'll come back and then have questions in person.
No neutrinos from black hole mergers. The same issue. You have two independent event horizons that merge and create one event horizon. So neutrinos cannot get emitted. There is nothing coming out of black holes. There can be theories that we don't have any observational proof of. So that if, for example, if the event horizon is not quite truly event horizon, so there are like hairs of black hole coming out of the event horizon. So there is this no hair theory. So this is one of the nice naming by astronomers. No hair theory and hair theory. So unless if there is no reason to believe that there are hairs of black holes coming out of the event horizon. If there are no hairs, black holes are bald, then there are no neutrinos. The second question was, can this constrain quantum gravity? Yes, and a lot of groups are actually working on theories, or basically fine-tuning the constraints from their theories that in some limits can explain the observations as we see them. So far, I do not know about any big splash success. But yes, people are thinking about it and working on it.
Thank you, online audience. Here we stop for the online audience, and we'll all have a cup of tea and then come back. We have very small time, I think maybe less than half an hour or so. So let's come back as soon as possible, please. Yeah.
Thank you.